Hi everyone, I'm Fred from the Australian National University. Today I'll be talking about our most recent work on exploring the predicate visual context in detecting human-object interactions. I want to first quickly go through the problem definition. So human-object interactions, or HOIs, are defined as human-predicate-object triplets. Naturally, to detect such a triplet requires the localization of interactive human-object pairs and the recognition of the associated predicate. Below are some examples. The localization takes the form of bounding boxes, while the recognition is a multi-label classification problem. Detecting HOIs could be very challenging, because the relevant visual context for a complicated interaction is very hard to learn directly. As shown by the visualized attention weights in the first figure, a competitive method in the literature fails to locate the relevant visual context and thus cannot detect the human washing bike triplet. Instead, many methods use object visual features extracted from object detectors to construct the representation for human-object pairs. As shown in the two figures in the middle, these object features are often extracted from object extremities, and therefore might lack the visual information to recognize the predicate. In this work, we propose a method that focuses on the predicate visual context to tackle this issue. We adopt the two-stage detection paradigm in this work. We first use data to detect the humans and objects in a scene, and then construct human-object pair representations by fusing the object visual features and a spatial representation based on their bounding box coordinates. We use this representation as the query in a subsequent decoder. As these queries are constructed instead of learned, we refer to them as explicit queries. In this triplet decoder, we propose to guide the cross-attention mechanism using the bounding box information as spatially inductive bias. To elaborate, let us first revisit the dot product attention mechanism with positional embeddings. We will denote the keys by key sub C, as they contain the visual content features of image patches. We also refer to them as the content keys. In addition, we denote the positional embeddings for the keys by K sub P, and we refer to them as positional keys. Similarly, we have content queries and positional queries, and the dot product attention can be expanded into these four terms. As we will show later, these two cross terms in the middle produce mostly noise. Therefore, we instead concatenate the positional features and the content features, following previous practice. For the other two terms, the first term measures the visual similarity between the keys and queries, while the last term measures the spatial similarity, which is what we will focus on next. Since the positional keys are formulated as sinusoidal embeddings, we use the same sinusoidal function for the positional queries by encoding the box center coordinates. For a single box, this expands the spatial similarity terms as follows. Here we also modulate the term with the box width and height. To extend it to bounding box pairs, we simply concatenate the positional embeddings of the two boxes, which is shown mathematically to be equivalent to spatially summing the corresponding attention weights. Here we show some visualizations of the individual terms in an image with the interaction person washing bike. In the first figure, the visual similarity term has high activation around the water hose and an irrelevant bike in the background. The spatial similarity term in the second figure adds a bias towards the human-object pair. These two terms combined result in high activation mostly on the water hose, which is the key to recognizing the predicate washing. And as promised before, we show in the second row that the two cross terms produce mostly noise. Quantitatively, our method outperforms previous state-of-the-art with the same backbone. And as a two-stage method, our method can benefit from the recent development in object detectors, which significantly boosts the performance. Thank you for tuning in. You can find the codebase of this work using the QR code below. Have a good day.